before entering the trade.
Okay, so does that go alongside work then? Do you work somewhere and go to technical school at the same time, or is it you do the technical school and then go and kind of get a job?
A lot of times that's the case. A lot of times, especially when we become older high school participants, our junior and senior years, a lot of us are allowed to go work in what we call a cooperative situation, where we can go rather than be at school and rather than be in that VOTEC facility. We're allotted time to go spend time at a traditional job and earn money at the same time as on the job training.
Okay, yeah. So kind of similar to an apprenticeship, what we would call in the UK, really.
Yes. And just more of a short-term basis, only part of your day traditionally.
Oh yeah, yeah. Okay, so where were you working first then, and what were you doing? Is it just?
Well, I began my journey, if you will, at an Oldsmobile dealership here in the United States, and that's a car that General Motors used to produce, a line they used to produce. No longer is it available, but that's what they used to produce. And I was pretty much learning how to navigate my way through the shop, learning how to handle tools and what these tools do, and basic service procedures and minor inspections, if you will.
Okay.
After that, I'll call it my college career began. So I would spend 8 weeks at a college learning at the dealership level, how factory dealership technicians are trained for 8 weeks at a time. And then I'd go back to my hosting dealership and I'd practice the techniques that I've learned and things that I've learned about the systems I'd be addressing.
So similar to like receiving dealer training, really, is that right?
Yes, exactly it. I was able to certify out of certain classroom areas just as a dealership technician would. So I actually entered the dealership as a professional dealer technician at the age of 19.
Right. Yeah. Okay. Cool. So I suppose that was similar for me here then. So I started from the age of 16 into an apprenticeship, working alongside the college, and then I suppose by the time I was 19, I was fully qualified and treated as all the other technicians. So I suppose although they're quite different, they all kind of work out in the same way in the end.
That sounds about right. Very similar.
Yeah. Okay. So what is it you're doing now then? What's keeping you busy in the week?
Well, I was a technician full time for many years, better part of 20 years, and it's such a small world. I recognize a couple of names on this presentation, John Lampla, for instance, and I'm not sure if my good friend Danny's here, Dan Perney. I just see Dan, but believe it or not, we used to work together at the same dealership. Matter of fact, a lot of the stuff, the training path I put myself on was because of these two knuckleheads.
Wow.
I seen if you apply yourself, they did things so fluently at the dealership. They knew so much. That's the person I wanted to be when I grew up, so to speak. So I really got to thank guys like Dan and John for providing that path for me to follow. If that makes sense.
That's great. Yeah, privileged to have them in our community as well. Great contributors to what we're doing. So
excellent.
Yeah, such a small world, eh?
Sure is. And once I found out who's that they were going to be in this presentation, I had to chuckle at it. Excuse me.
What would you say were some of the main things that you did to help improve your diagnostic skills and learn how to get into some of these more, I suppose, what we could call advanced diagnostic techniques?
Well, I'm sure John and Dan will agree. Most of what we learn at the dealership level is about the cars, the specific vehicles we are addressing. And many times I feel is that we don't know enough. We know what we need to know to fix that car. But if I were to take that car out of my work bay and replace it with a car I was not familiar with, that skill set wouldn't necessarily apply to this new vehicle. So I spent the first probably half of my career learning like that. And I realized after attending some aftermarket, what we call aftermarket training, the ones that were provided not at the dealership level, but for the aftermarket service technician, they learned differently. I felt they had a bit more knowledge than we did at the dealership, simply because they were forced to understand how things really worked rather than how the system works on this particular vehicle. So
Yeah.
once I started stepping back and realizing what that entailed, I realized I needed to understand the physics involved. Instead of understanding how for instance, a Honda ignition system worked, I had to step back and say, how do we make a spark?
Okay.
And
Yeah.
that knowledge could be applied to anything, if that makes sense.
Yeah, definitely. I mean, I suppose I had this similar experience having done, my whole apprenticeship and, the following years at BMW. BMW was all I knew. So, yeah, to actually have friends come up to you and ask, I've got this Honda with a problem, or, Toyota or Volkswagen, you kind of like, a little bit nervous to actually commit and go and work on it. You get used to all these common issues that you see working in a dealer, and the common systems and circuits and things. Um, similar to yourself, I didn't really go into taking aftermarket training, but I think what opened my eyes was when I got a taste of working in the independent world. So, you're in the independent world, you haven't got the backing of, the dealer tools and the support and, the wealth of knowledge around you. And you're kind of almost on your own and have to start improvising a little bit. And I do absolutely take my hats off to the guys in the independent world who are working on everything, because, like you say, they have got to work differently and
Really do.
approach things differently.
They extract a lot more usage out of the tools they have at their disposal, and they certainly understand at a deeper level. And I could say that because I've seen both ends of the spectrum.
Yeah.
And
Yeah.
I think if I were to re-enter the industry at a more focused point, like at the dealership level, I think I'd be a far better technician to the dealership today than I was 10 years ago.
Yeah. With that different outlook on just
Yes, with that
approaching
different outlook.
diagnostics in
Exactly.
general. Yeah. I mean, the other guys to think about are those roadside guys. They've
Oh,
got to
boy.
go out to a car and they've got a customer just standing there, watching them, speaking to them, asking what they're doing and all that kind of thing. So, that's another level again. And, they've only got whatever they can carry around in their van.
It's true. I do that on the side as well. And that's a challenge in itself. Just
Yeah.
not
So
always
they've got to
having the
get them on
tools
the
you
road.
desire.
Yeah. So most of my family were, most of my family were in the auto trade at some point or another. But, my dad was an AA roadside patrolman. So the AA is like one of the biggest roadside assistance businesses in the UK. His brother as well. So my uncle was the same. He actually went on to be a trainer. And my granddad and his brothers, they all had mobile mechanic businesses. So they had like a sun tester in the back of the van. And that's what those guys were doing quite a lot. And, some of the chats that we'd have would really be about, the basics, the fundamentals, which, like you say, is that's what you need to have a good grasp on if you're putting yourself out there in that kind of world.
Sure.
Cool. So all the guys then that are in the mechanic mindset community at the minute, we're all about oscilloscopes. So most of what we are talking about at the minute is picoscope. However, I've seen that you're quite an advocate of e-scope oscilloscope. So is it the one that Bernie uses?
Yes. And for a good reason. It's because I've worked closely with Automotive Test Solutions for many years. I've been a customer and a friend of the company and have beta tested for them. But I'll be the first to tell you, I'm not a salesperson at all. And I'm not to advocate any one scope. The techniques we're going to be talking about today are easily applicable to almost any lab scope out there now. Any PC-based lab scope that can store data and has a decent enough buffer where we can store some data over time. So yes, I would never be the guy to tell you it's better to have this scope than that scope. Every scope has its ups and downs, and it takes us being familiar with the tools we're using to know their limitations, what they're capable of and what they're not capable of. If that makes sense.
Yeah, sure. Yeah. It's really, I suppose the best scope for you really is, if you're getting started, is the one you can afford, isn't it?
Honestly, I'll take that a step. It's the one you're going to use. So
Yeah.
I would rather buy a scope that might be outside of the range I want to spend at this point in time. But like I see people all the time say, I want a starter scope. And my response to that is, well, you're going to outgrow it in 6 months and it's going to lose value, just go for the, if they were going to buy a single channel scope, just go ahead and buy the four trace scope now. You won't regret it.
Yeah. If you're serious about getting into it, then kind of go for it.
Exactly.
Okay, cool. So we're going to have a look at this in-cylinder pressure testing now. So Brandon's prepared a bit of a presentation for us. We're going to walk through a basic overview of what the test is about and some of the main points that we need to be looking at when we're analysing the waveform. Then we'll go on to a bit of a case study. So if at any point you want to ask any questions, if you just use one of the reactions down below to raise your hand, and we can unmute you and you can unmute yourself and ask the question. We are recording this as well, so we can create the lesson inside Mechanic Mindset after, and we'll also be doing a short YouTube video of it as well. So over to you then, Brandon.
Excellent. Two questions. First of all, Darren, would you mind minding the reactions and people's questions so you can just stop me?
Yeah, sure. Yeah.
And second, I asked, can you see my presentation currently?
I can. Yeah. Yeah.
Okay, excellent. I just wanted to make sure. Okay, guys. Well, guys, thank you very much for joining us today. As Darren mentioned, my name is Brandon Steckler. I'm with Motor Age Magazine as the technical editor, and I'm an instructor for both CarQuest Technical Institute and World Pack Training Institute. But more important than that, I'm still a technician just like you guys. And as you heard me mention earlier, it was the first probably half of my career, maybe a little less than half, that I spent fumbling around. I was pretty good at what I did, but I realized shortly thereafter that I was just very familiar with the cars I was working on. And again, if I got away from that car, that Honda I was familiar with, and I was faced with a Volvo or a Jaguar or a Saab, I was lost. So I attended some training in the aftermarket side and learned basically my approach was wrong. When I say wrong, I don't mean totally incorrect. It just wasn't the most efficient. So learning to apply techniques that allowed me to understand the physics involved and how things worked, and maximizing my tool usage, as well as knowing what that tool can and cannot do, the right tool for the job. I became more efficient, and I learned how to fix cars better and be more accurate. And one of the things I focused on most was what tools and techniques apply to almost everything. And I hope that makes sense to you guys. In other words, I want to purchase a tool, no matter how much that tool costs. I want to purchase the tool that I can continue to use over and over again on different vehicles, rather than buy an expensive tool that only works on one vehicle line. For instance, I would much rather have a capable lab scope than maybe a factory scan tool. Although sometimes it'd be beneficial to have that factory scan tool, that lab scope applies to everything with electrical impulse. So I'd rather have that. With that being said, I gained some insight from these classes I was taking, and from this in particular individual that was teaching me. His name was Jim Morton. And I learned the most important lesson I learned from him was how to learn, how to be a self-learner and continue my own education my way by learning how and where and what to read and what techniques and tools to master to be applied to any vehicle I'm faced with. So again, going back to the physics, I realized an internal combustion engine is virtually the same. When I say an internal combustion engine, I mean a 4-stroke internal combustion engine. They're the same no matter what vehicles we're working on. True, it's nothing more than an air pump, and we do play games with camshafts, and we play games with variable cam timing and variable lift and duration. And yeah, we can add a turbocharger to maybe force feed these cylinders and alter the exhaust configuration to help this air pump, this engine, breathe better. But ultimately, it is an air pump, and it's the physics we have to wrap our heads around to get a full understanding. So that's where I came up with the idea for this class: pressure waveform acquisition and analysis. And I call it from the inside out, is because it's very true that the pressure pulses that we can monitor and observe at the tailpipe, or inside the crankcase, or in the intake manifold, or in some cases, even in the cooling system, they all originate from within the combustion chamber. So that's where the idea for this name came from. Now, understand this is written to be an 8-hour class, and we are certainly here just to simply touch on the subject to give you guys maybe some interest or to see where my frame of mind, the method to my madness comes from. So that's exactly what this little snippet of the class is designed to do. As Darren mentioned, I welcome any questions, and I hope we can, I hope you guys choose to speak up and not be bashful about it, because if one person's thinking it, I guarantee at least 10 more have a very similar question. So the first place we got to start off is what a pressure transducer is. Now, a pressure transducer is nothing more than a device that allows us to take this physical quantity, pressure, and convert it to an electrical signal. So we can see it on our lab scope, drawn out over time, graphed out over time. Now, we should be very familiar with this device because we see it on many vehicles. We've got our 3-wire pressure transducers, our manifold absolute pressure sensors, our fuel tank pressure sensors, in some cases, air conditioning, right? AC pressure sensors and oil pressure sensors, they all do the same thing. They take a pressure quantity and convert it to an electrical signal. So when we use this information and plot it on a lab scope, it yields us some data. It yields us a physical, a drawing, a visual representation of what pressure is doing over a course of time. And when we understand how those squiggly lines get on the lab scope screen, then we can begin to understand why they are there and what they represent. And I mention that because of this. Some of you may or may not be familiar with this name, a man by the name of Mac Vandenbrink. Matt Vandenbrink, I think, said it best. He said, being able to explain something to a 6-year-old and have them understand is true mastery. So rather than trying to have a big, thick reference manual like this with all the possible faults and events that could occur in a pressure waveform and having to either reference that manual or memorize it, why not understand how the squiggly lines get on the screen so we can make decisions on the spot after careful analysis, just like a doctor analyzes an X-ray. So when it comes to pressure waveform analysis, there's basically 2 different types of pressure sensors. What we're going to be talking about today in the short time we're going to spend together is an absolute pressure transducer. The other device is known as a delta pressure transducer. And the difference is as follows. An absolute pressure transducer measures actual pressure. In other words, it's going to give us an electrical quantity that equates to a certain pressure. Like we can reference it to a chart if we wanted to. I call this one a positive absolute pressure transducer because it's referencing pressure in a positive fashion. There are also negative pressure transducers, and they both function exactly the same way, meaning the positive and the negative referenced pressure transducers function the same. The only difference is how they are plotted out on the screen are going to be inverted from one another. So if I'm using a positive pressure transducer and I were to take a hose and pressurize it with shop air, I should see the waveform begin to climb in amplitude on the screen. Whereas if I was using a negative pressure transducer, or what we call a vacuum transducer, it functions exactly the same way, but it's inverted. So if I put air pressure in that hose again, it's going to make the trace go south, go negative in amplitude on the lab scope screen, because it's referencing negative pressure. Positive is opposite of negative. So as I've mentioned, as pressure increases, so too does the amplitude of the signal. And as pressure decreases, so too does the amplitude of the signal. We don't typically have to worry about that, those of us that are using Pico devices, because the Pico WPS 500 is indeed a positive pressure transducer. So positive pressure, positive signal. Negative pressure, or what we like to call here in the United States, if you're not a scientist, is vacuum. I know the word vacuum isn't truly the correct word to use, but this is what us mechanics call vacuum over here. Anything less than absolute pressure, we call vacuum. So the waveform is going to climb with pressure. Now, these require a reference voltage and a reference ground. That provides that range for that sensor to operate, again, just like a map sensor or a fuel tank pressure sensor or any other pressure transducer requires that range of operation to function on. It's that third wire, that signal wire coming from the transducer going back to the lab scope that we are going to be interested in. Now, the delta sensor, that word delta, does anybody know what that word means? Delta refers to the word change. And what I mean by that is the delta transducer is not like the absolute transducer. It cannot give us a value of pressure, no matter what it is, or a value of negative pressure or vacuum. It could simply respond to changes in pressure. And it makes it an extremely valuable tool to use alongside of a pressure transducer of an absolute configuration, because it's very responsive to change, whereas the absolute pressure transducer does not respond as swiftly. So we can use delta transducers to reflect very minute changes in pressure, and positive pressure changes are going to cause the sensor trace to climb on our lab scope screen, and negative pressure changes are going to cause the signal trace to decline or negate on our lab scope screen. And the kicker is the amplitude of that sensor output is proportional to how intense the change we experience is. So if we have a very large, rapid change in pressure, the amplitude is going to exhibit far taller than if the change was less intense. So this gives us a good idea of proportion, how rapid or how intense the change was. So rather than try and dissect those words I just shared with you over the last 3 minutes, how about we conduct a little bit of an experiment, if you will. So what I have here is I've simply taken an absolute pressure transducer that you see here on the left side of the screen, again, like a 3-wire map sensor. And on the right side of the screen is this delta sensor. So the way this delta sensor works, I can't remember, is pressure changes come into this, I'll call this the sense side of the sensor. There's a piezoelectric crystal inside, and that piezoelectric crystal responds to agitation or vibration. So the harder the agitation is acting upon the crystal, the more intense that amplitude becomes. So again, having this transducer, both these transducers, the delta and the absolute, connected to the same hose here in the center, any pressure changes I make to this hose right here are going to impact both of these sensors' operation simultaneously. Now, what I've done here is I've connected this to a lab scope. Now, one thing you got to understand here, this is what we call a dual scope. And basically, I have 2 lab scope screens on the same PC screen here. Now, up top here is the absolute pressure transducer, and on the bottom is the delta. So I need you to do me a favor. For the first few minutes here, I want you to ignore the bottom half of this screen. Let's see if I can do this here. Let's just focus right up here. So again, what we have here is a 0 point. Picture this like your map sensor referencing atmospheric pressure, okay? The output of that sensor currently is at 0. Now, if you could picture that sensor I had connected to those 2 hoses and to that one common hose, if I were to take that hose and suck on it and put it into a state of negative pressure, like a straw, suck it down into a negative state of pressure, the output from the sensor is going to decline like you see here. And we could clearly see that I am maintaining that negative pressure in the hose. So what do you think I did here? If this represents a point when I drew a vacuum on that hose and I plugged it, what did I do right here? Does anybody want to chime in? I'm not sure, Darren, do you have the microphones enabled? I don't recall what we decided to do.
If anyone wants to join in, then if you use the reactions button here to raise your hand, like I have just done there, it's at the bottom of the screen. It's called raise hand, or even get in the chat. Okay,
well, there we go. Pete
Sean's
Sullivan. Can you turn on Pete Sullivan's microphone? He's got his hand up. Pete, what do you think that means? You've got to turn on. You've got to unmute yourself, Pete. If you click on your name, there should be an unmute button. Perhaps not. Maybe he doesn't have a microphone. But in essence, oh, go ahead. Whoever just said that.
I've just changed it now. Yeah, so people can unmute now. Yeah.
So I pulled this into a vacuum and I've held it with my thumb. What happened right here? What did I do here with my thumb?
Release the vacuum.
Right. I've taken my thumb off there and I've allowed that hose to equalize to atmospheric pressure. So if I go from a negative pressure to a positive pressure, of course, my trace is going to head north and it's going to stop right at the 0 mark because we're at atmospheric pressure. So then for good measure, I waited a few seconds. And what did I do right here?
You blew into it.
Right. I've pressurized that hose and I've pressurized it and I've held it again with my thumb. And I've trapped that pressure in the hose, but then I did something right here. What did I do? Right, I've taken my thumb off the hose. And when I did that, the pressure that was in the hose, it bled out and my hose is now equal to the pressure in the room around me. So it's clear to see, right? We can wrap our heads around an absolute sensor and how it works because it just makes sense. Now let's take a look at the delta sensor. Now, keep in mind that delta sensor is connected to the same hose. So everything I do to this hose that happens to this absolute sensor is happening to this delta transducer at the same exact time. So what we see here is this. Remember, delta means change. So if I pull this into a vacuum, we go from atmospheric pressure to a negative pressure. Of course, this is going to represent a negative change, and everybody agrees with that. But here's the weird part. I'm holding negative pressure. I'm trapping it in the hose here. Why did this sensor value return to 0? Anybody have an idea? If I went from a positive pressure, if I went from atmospheric pressure to a vacuum and I held it, of course, this shows a negative change, but why did it swing back up to 0 again? I'll give you an idea, a clue here. It represents change.
Yeah, so the people in the chat have said, yeah, there's no more change.
Okay.
It stopped changing. So it's kind of gone back.
Okay,
Yeah.
good. I've inadvertently closed my my chat box. That's why I didn't notice it. But you're absolutely right. We stopped changing. We're now maintaining. So a few moments later, I let that negative pressure out just as I've done up here. And of course, we see a positive change. We go from a negative to atmospheric. That's a positive change. And then it returns back to 0 because it stopped changing. We're now maintaining atmospheric pressure. And of course, I blew into the hose here. And as you can see, there was a positive change, but again, returned back to 0 because we maintained positive pressure. It's no longer changing. And then here, I let the pressure out of the hose and we equalized back to atmospheric pressure. So we went from a positive to atmospheric. And of course, that's a negative change and we refer back to 0. So as you could see, these are two different type of sensors telling the same story, just in a different language. I hope that makes sense the way I put that. So when this really hit me, it was like a ton of bricks. We can use pressure transducers, whether we're using absolute transducers or delta transducers. We can use both of these sensors tandemly in different areas of the engine, the exhaust system, and the induction system as well. We can use it for in-cylinder pressure testing. We can test pressure within the intake manifold, the tailpipe, the crankcase, the radiator, and do all these simultaneously and plot them out on a multi-trace lab scope screen so we can make diagnostic decisions about the engine's ability to perform, or each individual cylinder's ability to perform, whether it has integrity or not, all at the same time. Now, I want to talk about this for a moment. Many of us, most of us, have been using mechanical gauges for decades, and certainly it gives us a lot of information. But when we're talking about a gauge on a hose connected to a cylinder with a Schrader valve, a one-way check valve, what does the gauge tell us? When we insert a gauge in place of a spark plug, for instance, on a petrol engine, and we crank the engine over, what is that gauge displaying? What is the limitation of that test? What does it tell us? It's right. Vince, everybody, Matt, Cherry, they all said the same thing, is that it only shows us maximum pressure. Exactly. So my point is this: if I crank an engine over, let's say 15 complete cycles, crank, and every cycle produces 100 PSI, pounds per square inch. 100 PSI of pressure, but on the 8th cycle, an exhaust valve fails to seat intermittently. And that cycle only yields me 40 PSI of pressure. What is my gauge going to show me? It's still going to show me the 100 PSI. Yeah, we're going to, because it's trapped behind that Schrader valve. So for that one reason, I don't like to use a gauge. Will I use a gauge? Certainly, but I have to understand the limitation and that I could still get let down by that gauge. So why I choose to use a pressure transducer besides that fact right there is that it allows me to plot this information over time in a graph format. I certainly love graph formats because it allows me to see a history of what happened in the past. I don't have to catch it momentarily. So if I was staring at a gauge and I didn't have a Schrader valve in that gauge, and on the very next cylinder, I had a pressure transducer, my pressure transducer would reflect maximum pressure and then everything in between maximum pressure and minimum pressure over time, whereas the gauge would only show me a needle that would flicker. And I'd have to have my eyes fixated on that gauge to capture that, if my eyes were fast enough to capture that. So unlike a gauge that only shows peak pressure when coupled to a Schrader valve, the pressure transducer shows me everything in between. The valve events, the breathability of the cylinder, how that cylinder inhales, how it squeezes, how it exhales, and everything in between. It works with other inputs and tools. For instance, the picoscope, we should all be familiar with the cursors available. We can utilize both horizontal and vertical cursors to make diagnostic decisions and yield information from the data that was yielded to us from this lab scope capture. And compare it to the 720-degree engine cycle, or 2 rotations of the crankshaft, 1 rotation of the camshaft. It allows us to provide correlation in time with these events in degrees. So what this yields me as a diagnostician is rapid and preliminary verification. And John Lamp and Dan, you guys, we've been doing this for years. Lots of times we have this information within just a couple of minutes, conclusive evidence, in fact, that this engine needs to be disassembled. Even if it takes 20 something hours to disassemble this engine, we can go in there with confidence because our lab scope captures have showed us there, have led us there. And believe me, there's no worse feeling for me than taking the front cover off an engine, crossing my fingers, looking down and hoping to see a problem, only to find out that, whoops, there's nothing visible. I hate that feeling. So never again will I shoot from the hip like that. I'd much rather employ these techniques that we're talking about here today. So getting a diagnostic direction and knowing, as a matter of fact, that this engine has to be taken apart without question is what makes me sleep better at night, rather than hoping and taking something apart for no reason. So this truly became power for me once I realized what it could tell us. We can clearly see, with a little bit of training and some studying and some practice on known good vehicles, we can see valve sealing issues, compromised piston rings and cylinder walls, damaged connecting rods that are bent and allow just for a few changes in degrees of crankshaft rotation to cause a misfire with no real loss of compression in any way, shape, or form. It becomes completely visible on a lab scope when captured with either an ignition event or a crankshaft position sensor input.
We could get that with like water, ones that have taken in water in the UK. They drive through the floods,
yep,
diesels, and
they hydrolock and bend a rod. Some of them are bent just minor, but it's enough to disrupt the combustion process. And even though there's nothing wrong with the cylinder's integrity, so it becomes very difficult, but it's seamless when using a couple of inputs. With today's GDI platforms, gasoline direct injection, we know carbon has become one heck of an issue, especially since most customers do not maintain the vehicles like they're supposed to be maintained. Carbon issues and valve restrictions are easily visible with a simple snap throttle test to infer how the cylinder inhales as well as how it exhales. We can monitor camshaft phasing dynamically with variable valve timing. We can see compromised valve lift and duration due to cam and lifter wear. I mean, it makes it look like crystal ball diagnostics. The slightest bit of camshaft lobe wear when compared to a known good cylinder, it sticks out like a sore thumb, and it's extremely visible. And to the untrained eye, again, you look like an absolute magician. We can see ignition timing. How many of us have experienced a torn crankshaft balancer when the innards become separated from the outer ring, and the input for the crankshaft position sensor becomes retarded relative to the actual camshaft position, crankshaft position. The vehicle exhibits itself with low power, and this thing will get everything from a tune-up to a fuel pump to a timing belt, and the car is never fixed. But until you take a look at it with an in-cylinder pressure transducer and compare that to an ignition strike, you'll see the ignition strike is occurring 20, 30, 40, 50 degrees later than it's supposed to. And it's, again, very visible without taking anything apart. So with that, I really wish we can get into all of the nuts and bolts of this class, but I've tried to pick out a few points of view to give you guys just a taste of what this can do for you. And I want to start off now by describing how to pick apart an in-cylinder compression waveform. So we're going to talk about the anatomy of the waveform. And again, if you have any questions, please feel free to stop me. So before I transition into that, I want to make mention that this is not about advanced testing. This is not about doing the difficult stuff that not everybody understands. This is about making things easy. In-cylinder pressure testing is not difficult. It, just like anything else, excuse me, it takes a level of understanding. So the one point I definitely want to hammer home is, guys, we're still using a lap scope. A lap scope is nothing more than voltage over time. However, this time we're testing in a domain for pressure. So instead of voltage over time, we're looking at pressure changes over time. It's as simple as that. And that's exactly the way I want to keep it so we can all understand. Now, the one mistake people make, especially when getting started with this, is they're always considering pressure, but they're never considering volume. And here's what I mean by that, if you give me a moment to elaborate. Just like electricity, where voltage is the electrical pressure and resistance is that opposition to current flow, any change in voltage or resistance is going to automatically yield a change in how much current flow we have. So when it comes to pressure waveforms, I want you guys to think in terms of volume. Pressure is the result. In other words, if we have a volume and we change the area, I don't know if you can see my syringe here, we change the size of the area, no matter how much air is in there, the pressure has to change. So keep that in mind. I'm going to use this syringe. I'm sorry, it keeps disappearing in my virtual background here. I'm going to use this syringe to describe just that, because I'm a mechanic and I've held many of these things in my hand my entire career. And I know what's going to happen if I put my thumb over it and I try and move the plunger. I know what it's going to feel like. So we're going to move forward with that. Again, Darren, if you wouldn't mind keeping your eyes out for questions, I'm just going to stay focused on the presentation because I struggle to walk and chew gum at the same time. So this syringe, again, if I were to hold this thing in front of me, in front of the cameras, you guys see it, hopefully, and I keep it just like this. I've got the front of it exposed to the atmosphere here, and this plunger is fully extended. Relative to the pressure in this room around me, how much pressure would you say is in this syringe? How much pressure differential is there between the room I'm in and the syringe?
Zero.
Yeah,
it should be
equal, none, zero. Yeah.
Right. There should be no difference in pressure. Now, for the moment, let's factor out heat. We're not talking about heat and expansion. Just pretend that's not a factor. If I were to take this plunger, this syringe, and plug this off, and I take this plunger and I push it up all the way, assuming I could do so without letting any air come out. First of all, what happens to the area inside the syringe?
Decreases.
Right. The area decreases. So if I have a certain amount of air mass, a certain amount of grams of air inside this syringe, and I plug this off, does the air mass change? Does the gram value of air mass change? It doesn't,
No.
right? It's still the same amount of air, but because the area got smaller, what happened to pressure? It's just physics.
Increases.
Right? The pressure had to go up. That's just physics. We all understand that. Now, assuming I'm back at this position and we've built a significant amount of pressure in there. If I did not take my finger off of this syringe to relieve that pressure, I kept it sealed, and I simply returned this plunger right back to the where I started from, that exact position. And again, no air got in and no air got out. What would my pressure be back again at this point in time relative to the pressure in this room?
0.
It would be 0 again because there was no change in gram air mass. Now, that's pretty much this situation that I have on my screen here that I've just described to you. Would everybody agree with that? Please raise your hands if this drawing makes sense with what I just said. It correlates with what I just said.
Yes.
Excellent. Okay.
Yes.
So now we're going to change it up a little bit because I want to prove a point. If I take this syringe now and I repeat that process, but instead of let's pretend on the scenario you see on the screen here that I produced 100 PSI here. We're going to use nice round numbers. On this next case, I'm going to repeat that process, but I want you to listen. You hear how some of that air got past my finger? Everybody hear that?
Yeah.
Okay, so instead of 100 PSI, let's pretend all the way to the top here, I have 80 PSI. Now at 80 PSI, it's less than 100, but watch this. If I start to return my plunger, again, nothing else leaks out as I return the plunger back to where I started. I go from 80 to 70, to 60 to 50, to 40 to 30, 20 to 10, 10 to 0. Look where my plunger is. Did I return to the bottom? I didn't, and I'm at 0. More importantly, what's going to happen when I continue to pull? The area is getting bigger, but I can't let air in. I'm going to go into a state of what I described earlier as vacuum. Again, I know that's not technically correct. It's not technically correct, but vacuum means negative pressure in my world.
On its
So
way to a vacuum.
Right.
That's what I like to
It's on
say.
its way. It's negative pressure. It's below
Yeah.
atmospheric pressure. Excuse me. So the same happens. It's the same concept that we have to adapt and employ when we are analyzing pressure waveforms. We got to understand if there's a volume loss or not. So before I go any further, I want to remind you guys, a lab scope is nothing more than plots of data over time. Anything that happens to the left side of the screen is early or advanced relative to something that is happening to the right side of the screen. Anything that's happening to the right side of the screen is late or retarded relative to what's happening on the left side of the screen. So we just have to keep that in mind when we move forward. So I want to talk about the different strokes now, the 4-stroke internal combustion engine. And for me, this is funny. I don't know if it means anything to you guys over in the UK or the other parts of the world, but this is just a joke. So many people want to know how this relates to in-cylinder pressure waveform analysis. And again, this is how I understand it by looking at the syringe and how I described how it just functions. So on my screen here is a running at idle, perfectly healthy in-cylinder compression waveform. And first we have the 4 strokes. We've got as pressure increases to its highest point here would represent top dead center compression. And as the piston decreases, what would we typically we would call the power stroke is I'm going to refer to now as the expansion stroke, simply because there's no combustion taking place in the cylinder. We've removed the spark plug from the cylinder, and this is simply the crankshaft dragging the piston and rod assembly down the bore of the cylinder. And then when we get to bottom dead center, as far as that piston will go, the crankshaft continues to rotate and our piston will change directions and go up on our exhaust stroke. And this lasts 180 degrees till we're at top dead center again. At that point, once again, the piston will change direction. We will enter our induction stroke until we hit bottom dead center, which would be 540 degrees. And then we go back up on the compression stroke again and repeat the cycle. So top dead center to top dead center represents 720 degrees of crankshaft rotation. Now I want you to watch my syringe as I re-describe this. First of all, I want to start at this part of the waveform, and I'm going to explain that in a minute. I know there's no numbers on this screen to designate pressure value as it regards amplitude here, but take my word for it. This is about 0 PSI, okay? Meaning anything below that is what?
To
Right.
pressure.
It's a negative pressure or a vacuum. Now, remember, this is a perfectly healthy running engine. So here in the United States, we like to use inches of mercury to represent pressures below atmospheric. It's just a common unit of measure, if you will. Just to give you a hint, about 1 pound per square inch equates to about 2 inches of mercury. So if I have 20 inches of mercury, that's minus 10 PSI. So I'm here at sea level. Here in the United States, I'm at sea level, and a good, healthy engine, a strong running engine that's sealing well, I would not be surprised to see 22 inches of mercury as idle, as negative pressure being measured in the manifold. As you guys know, manifold pressure is the result of the pistons inhaling air. They're trying to displace more air than that minimum rate throttle position will allow. Does that make sense what I just said? The pistons are the pistons are trying to inhale air, but the throttle restriction is so tiny that minimum air rate is allowing pressure to drop across that throttle plate. And we're evacuating that intake manifold of air. That's why it's in a negative state of pressure. So the moment my intake valve opens, pressure in the cylinder is going to be equal to pressure inside the intake manifold because they're touching each other now. Does that make sense? So watch this. This is manifold pressure. We're going to call it 20 inches of mercury. So when I do this now, okay, I did my example earlier, and I can't get it to show up on the camera. I did my example earlier looking at this, calling this atmospheric pressure. Remember, we said it's equal to what's in the room. Let's pretend this room I'm in, I'm sitting inside the intake manifold. So isn't there 20 inches of mercury in here right now? Does that make sense? 20 inches of mercury. Now, I'm going to close the syringe. I'm going to go up and squeeze this and squeeze this and squeeze this. And if nothing leaks out, I'm going to produce maybe 100 PSI of pressure. If I draw that piston right back down to where I started and nothing leaks out, that cylinder remains sealed, what should my pressure be? If I started with 20 inches of mercury, what should my pressure be when I extend it again?
It will be 20 again.
Yeah, got 20 in the chat. Yeah.
So if I'm measuring that with a pressure transducer, and this is 20 inches of mercury, and then I go up on pressure and I come back down, shouldn't they be even? If this is 20 inches of mercury, shouldn't this be 20 inches of mercury? I'm just going to go over here because we're starting the process over again. If this is 20 inches of mercury, this spot right here is this spot right here. It's the same spot, just a different cycle. If I have 20 inches of mercury here and I squeeze it and nothing comes out, and I come right back down to bottom dead center, shouldn't I also be at 20 inches of mercury? This proves right here that there's no leak because they're even. If I had a leak, remember what happens to my syringe if I had a leak? Watch this. 20 inches of mercury. I go up, listen to my microphone. Some leaks out. Now watch this. What's fighting me here? You guys see that?
Negative pressure.
Negative pressure. This would pull far down here. Let me see if I can draw this here. This right here, instead of following this line, oh, it's glitched. It's not letting me draw. I'm supposed to be able to draw on this. I'm sorry, fellas. Here's my laser pointer. Let me switch back over to a pen again, and hopefully it will let me draw. No, for some reason, my PowerPoint presentation is not letting me draw. But this pocket right here, again, let me switch over to a laser pointer so it's easier to see. We start at 20 inches of mercury. We go up on compression. If nothing leaks out, we come down like this, and we should be at the same level as we are here. However, if there was a leak, we know this would pull way down here, right? Because that would represent the negative pressure that's fighting me right now. So all of a sudden, right before bottom dead center is the bottom dead center 180. This is pressure, and this is time. There is a rapid change in pressure in a very short period of time. What has to happen before a cylinder, a piston can expel exhaust gases out the port? What has to open?
Exhaust valve.
Exhaust valve. So if I'm at 20 inches of mercury, I go up on compression, I come back down at 20 inches of mercury, a state of vacuum, and I open the exhaust valve. What happens to the pressure in the cylinder? Shouldn't it equalize to the pressure in the exhaust? That's what we're seeing here. I got to get rid of this cursor. Stand by 1 second. This will drive me nuts. There we go. It moves a lot faster now. When this exhaust valve opens, that negative pressure in the cylinder is replaced by the pressure in the exhaust. It's sucked in. That's what causes this to rise. So what I'm getting at is, does this point right here have significance? I mean, right here. What does this point represent?
That the valve opening.
the exhaust valve opened. So then I go over here at bottom dead center, and this occurs about 45 degrees, give or take, before bottom dead center. Now I go up here on what represents my exhaust stroke. My piston is heading north towards the cylinder, and the contents are being expelled out the exhaust port. Doesn't it make sense that we are not building pressure?
Yeah.
So then
Yeah.
we get to top dead center 360. Oh, let me say that again. So assuming I had a restriction, assuming my exhaust ports were completely gunked up, or I had a restricted catalyst, or I let my ex-wife drive my car and she backed into a wall and crushed the exhaust system and my engine couldn't breathe, what might I expect to happen to pressure in this area here as the piston ascends towards the cylinder head?
It would increase.
Yeah, wouldn't we expect pressure to increase because the contents of the cylinder are being expelled into the exhaust stream, but the exhaust stream is not allowing that contents to leave the vehicle. So pressure would increase. So then I get to the 360 mark, top dead center, and all of a sudden the pressure drops. Why does the pressure drop? We just talked about this about 5 minutes ago. Why does the pressure drop right here?
That valve opens.
Right. And where did the valve open? Right here. The moment that intake valve opened, the negative pressure that's stored in that intake manifold, that storage tank at an idling engine, is exposed to the cylinder, pulling that cylinder into that same state of vacuum. Moments later, the piston starts to descend and it continues to draw on the intake manifold and draw air out of the intake manifold. That's why vacuum stays low here. And then we get to bottom dead center, 540. What happens to the piston after the 540 mark?
Goes up.
It starts
That's
going up.
right.
So if this is 540 and this is where the piston is ascending, how come pressure is not ascending here as well? What's still open?
Exhaust valve.
Inlet valve.
The intake valve. The exhaust valve will close shortly after top dead center. And I don't reference it because it's very difficult to see. We don't rely on that typically right here because it's very difficult to see on a normally operating engine. But my point here, even though the piston is increasing at this point in time, our intake valve is still open. So any air that's in that cylinder is going to be displaced back into the intake manifold. And that intake valve typically closes at about 55 to 60 degrees after this 540 mark. That's normal for that to happen. So my point is, what had to happen right about here?
Intake valve close.
Right, the intake valve had to close. So this point has some significance, doesn't it? And this point, that has some significance. And this point as well. And the fact that we have this graphed over time and we have active cursors that we can manipulate with our Pico 6 or Pico 7 software, for instance, we can determine 720 degrees. And we can also use our cursors to tell us how far offset this point is from a 180 mark, or how far offset this point is from the 360 mark, or how far offset this point is from the 540 mark, right? This is intake, or excuse me, EVO or exhaust valve opening. This is intake valve opening or IVO, and this is intake valve closing or IVC. All of these points of interest is something I typically analyze. When somebody sends me compression waveforms, I like to look at what I call here these points of interest. Now, we mentioned the even pockets and the significance. What does it mean if the pockets are even? When this,
There's no restriction.
there's no leak. There's no leak. That cylinder has integrity. When there is a leak and some of that cylinder charge is lost to another area, as that piston descends and we can once again draw back down, we will pull this pocket down further for, again, what you can see visually here. What's fighting me is negative pressure, vacuum. So that would cause this pocket to drop down further. But the fact that these pockets are even says that the cylinder has integrity and it is not leaking. It's sealed. There's no need to do a cylinder leakage test. We definitely want to see defined valve events. Remember, keeping in mind that this is pressure up and down and time, the definition of a good valve event is when pressure changes just like that, rapidly in a very short period of time. That information is yielded to us by a very rapid up and down movement, which would yield us a very defined point of opening. So if you could picture, if you will, I've got a can of beer here and I screwed a pressure transducer in that can of beer. If I open that beer slowly and it goes, shh, that would yield me a pressure waveform that would be very slow to change. And a slow change in pressure over a long period of time will be exhibited as a very round looking event. It wouldn't be nice and sharp like we see here. It would be round. But if I took that same can of beer and went and popped it instantaneously like that, that would yield us a sharp change. So we like sharp changes. Again, if there was a collapsed exhaust pipe or a clogged catalytic converter, if you will, this pressure would continue to increase. Darren, I want to ask you a question because you're the boss here. I know we discussed this being about 3 o'clock. I'm happy to keep going. I don't want to hold anybody up.
Yeah. Carry on. We're good,
Anytime you want to stop me, you let me know.
We're good.
Okay, so if we had any kind of restriction in opposition for air to leave this air pump, this cylinder, it would create back pressure, and that would cause this waveform to rise in this area. So this is no real back pressure. This looks good. We're darn near zero. One thing I want to mention here is good running compression. What is good running compression? It's very difficult to tell, and I'll tell you why. Depending on the cylinder's design, the stroke of the motor, the size of the bore, the temperature of the air, the position of the throttle, the speed of the engine, all of these things come into play to yield us what, and the geometry of the engine, how the engine's laid out. All of these come into play to tell us what good compression is. However, I don't care what the value is. I'm not going to reference a service manual and say, what is the specification for good compression? Everything I need to know is down here in this bottom half of this waveform. Everything I need to know. So if I've got a problem here, I will find a problem up here. If you had to rip this paper in half horizontally, the one I want is the bottom half. I don't care about the top half. Does that make sense? If we have a problem, we're going to see it down here in this area. The other thing I want to mention is straight towers. Now, again, this acquisition is drawn on a screen as pressure increasing over time and pressure decreasing over time. And if my crankshaft was rotating at an even, let's say 1,000 RPMs, just for descriptional purposes here, my piston should ascend at the same rate of speed as it descends. Would you all agree with that? Yes. So if I build pressure at a certain rate, I should lose pressure at the same rate. Meaning if I take that waveform and fold it in half, it should be perfect. It should match. That should yield me straight towers. And when I say straight, I mean symmetrical. And you shouldn't have to do this. Right now I'm using an E-scope just for simplification. If I took a horizontal cursor and I put it about halfway up the amplitude of that tower and a vertical cursor and dropped it at the highest point down to the bottom and used a second horizontal cursor to measure where this intersects this side of the waveform and compare it to the center, it will yield me about, in this case, 33 milliseconds. And then I did the same on the right side, and it's also about 33 milliseconds. There's only 1 millisecond of difference, not much difference. But watch what happens when you have a leak. When you have a leak, we repeat that process. I've got 21 milliseconds on one side and 16 milliseconds on the other. Do we see how that waveform appears to be tilting here?
Skewed.
Does that make sense?
Yeah.
We call this a leaning tower. There's more meat on this side than there is on that side as compared to this previous waveform. It's about even. So a leaning tower is caused by a loss of pressure in that cylinder. Now, I mention that to tell you this. You cannot always see a leaning tower unless it's severe. Just like we typically smell smoke before we see fire, you will always see uneven pockets before you see a leaning tower. A leak will give you uneven pockets. A severe leak will cause a leaning tower, but you will always have uneven pockets. Does that make sense? So I'm only showing you the straight towers versus the leaning towers just to demonstrate what it is I'm talking about. And the leaning towers represents pressure increasing at a certain rate. And instead of pressure decreasing at the same rate, it's decreasing at a faster rate. That's what causes the leaning towers here.
So what were you saying there, Brandon, that if you've got the leaning towers, you will also have the
Most
difference
definitely. Watch my fingers. If this represents the pockets, one pocket on one side of the tower and one pocket on the other, the exhaust pocket versus the intake pocket. As we get a leak, our pockets start to separate. As we get a severe leak, they start to separate more. The more severe it gets, the more the tower is going to start to be visibly leaning. So it's just a clue, but it's not something I lean on. It's just something for demonstrative purposes. So I can explain to you and explain why. So when it comes to in-cylinder waveform analysis, all we are really looking at is pressure changes over time. It's as simple as that. The waveform is referenced to atmospheric pressure, or what we call 0 PSI gauge pressure. Anything above 0 is pressure. Anything below that is negative pressure, or what I like to refer to as vacuum. The idea behind capturing the vents is to correlate the timing of the valve's opening and the valve's closing with the duration of that 720-degree engine cycle. If we know the 720-degree occurs from one tower to one tower, we can easily figure out how many degrees offset an event is occurring, and whether that event is on time compared to a known good vehicle or not in time compared to a known good vehicle or waveform. We're simply going to be monitoring these pressure differentials by moving air in and out of that cylinder and seeing how it reacts to the opening and the closings of the valves. So this is a dynamic type test. Now we can do this cranking, we can do it at idle, we can do it at slightly elevated RPMs or snap throttle conditions. And I even recommend power braking or brake torquing, what we call here in the United States, stepping on the brake pedal, placing the vehicle in gear, maintaining the vehicle's position, and very carefully accelerating the engine. The idea is we are opening up the throttle, but not allowing the engine to accelerate at will, because it can pump the most amount of air that way. That's the highest load you can place on a vehicle. And that yields us more visible restrictions. So I want to pull over here a sample waveform. But before I do that, does anybody have any questions?
We had one question in the chat there. It said, what PSI is not acceptable for the exhaust opening event in regards to exhaust restriction? So I'm assuming what's the maximum allowable pressure for the exhaust event? I think that's right. Is that right, Kumaran?
So what you have to keep in mind with that question is this: when we are measuring in cylinder, even though the exhaust valve is open and we are connected to the exhaust stream, we are technically measuring the pressure in the cylinder. Can everybody agree with that? So if I have pressure in the cylinder due to a restriction in, let's say, the exhaust port, or the exhaust valve lifter is collapsed and that exhaust valve doesn't have the lifter duration it should have, do we agree that that cylinder will be restrictive to exhausting? So technically the exhaust system itself in that case is not restricted, it's just the cylinder. So I have seen pressure in a cylinder go up 10 or 15 PSI under snap throttle conditions. However, there's nothing wrong with the exhaust system. That's sometimes why I reference power braking the vehicle, stepping on the brake pedal and opening up the throttle, because it allows for that momentary building of pressure because of that snap throttle, and then allowing the pressure in the cylinder to equalize to that inside the exhaust stream. So to answer your question, if I have a true exhaust restriction, I start to see drivability problems reflected around 6 or 7, maybe 8 PSIs when they really start to become an issue. But you're going to learn to get the feel for what it is you're working on. Because honestly, is a turbocharger not an exhaust restriction when it's not spooled up? It's sitting right in the way. It's sitting right in the way. In fact, it's the exhaust stream that propels it. So even the turbocharger is an exhaust restriction, but once it's spooled up, it's not. It doesn't have as much of an effect. So things we have to learn. We always have to be adaptive when it comes to learning, and rather than taking on facts, we have to start to analyze vehicles that are good and become familiar with that and newer technologies like that. Have anything else, Darren?
There's another one in there from Matthew Cherry. It says, what is the best waveform for analysis of valve events and pressure changes? So cranking, idle, snap, elevated, or brake torque.
You picked a very good question, and I would like to answer that question, Matt, in detail, because I dedicated a different portion of this class that we're going to get to in a few minutes describing that. And that'll be answered with this waveform I'm about to drag over and share with everybody. But before I do that, Darren, are there any more questions?
When it comes to analysis waveform, would you employ a different test for VVTI?
In other words, would I test a VVTI engine differently than I would a conventional engine?
I think so. Is that what we were saying there, Soren?
the first thing I would, assuming that's the question, the first thing I would keep in mind is that some VVT strategies are targeted and some are constantly moving. I'm going to give you an example of a lot of the vehicles I'm familiar with. They're targeted. So in other words, a vehicle will have the ability to phase the camshaft either 10 degrees positive, the intake camshaft 10 degrees, or maybe 18 degrees, or maybe even 25 degrees positive under full overlap. However, nothing in between. And then I get another vehicle, typically European vehicles, where it's constantly changing. It's constantly being phased back and forth to optimize breathability at any RPM. So it depends. The cars I've worked on, my experience, VVT does not typically occur at idle or cranking. I can't promise that on every vehicle. So it might mean making an acquisition with the VVT solenoids, oil control valves plugged in, and it may mean unplugging them and repeating the process, depending on the vehicle. With that being said, what about BMW and Valvetronics, where we may not play games with valve position, camshaft position, more so than we do valve lift and duration. And it's situations like that that really come into play that we have to be aware of. Not every vehicle functions the same. We have to be familiar with what we're working on, and that takes time.
And that you won't get the intake manifold vacuum either.
That's true.
Yeah.
That's true. And that allows the cylinder to breathe. It prevents pressure drops over a throttle restriction, which allows the cylinders to inhale at atmospheric pressure rather than fighting the manifold vacuum. So it's a process of efficiency is what it is. Makes the engine more volumetrically efficient. So I would like to, John Lamp has sent over, if I'm not mistaken, Johnny, right? If you wouldn't mind enabling your mic, John. You sent over a waveform of a vehicle. I think this is an 08 CRV that had a confirmed exhaust restriction. Is that correct?
That's correct. The car would not go over 35 miles an hour.
Now I got to ask you. Oh, go ahead. Sorry, John.
So the first thing I did was pull codes and had a couple misfires. I looked at the freeze data when it occurred, and I also looked at the map sensor, and I noticed that even when at high RPM, that map sensor really never changed. Put it up, banged on the exhaust, didn't hear anything. And then I took number one plug out, put my pressure transducer in there, and I could see at 3,500 RPMs, it was 28 PSI. The
Okay.
normal unrestricted one should be about 1.5 PSI.
So if
I
you're
did have another waveform that I sent it down that was, after the new converter was in, it was only like 1.6.
well, I'll tell you what, I've got both of your captures, John, the before the broken one and also the repaired one. So I'm going to drag them over. And Darren, if you will, let me know if you can see this. Can you see that? Is it opening up?
Yeah, we got
Yeah.
that. Yeah.
Okay. So what John was talking about was as follows. Now I will tell you, this is a home run. And John, I got to ask you honestly, when you put
Go
this
ahead.
transducer in, you were pretty confident you had a restricted exhaust. You just wanted to capture. Is that correct?
That is absolutely, look, I watched Scanner Danner's video. I didn't want to waste time. I didn't spend more than a half hour on this car.
That's awesome.
Yep.
So with that being said, John had a hunch, a strong suspicion he's dealing with a clogged exhaust. And this is pretty much the final nail in the coffin. He pulled out a spark plug, he inserted a transducer, and I'm going to venture to say, knowing the vehicle he was working on, from the point he opened to the hood to the point he had this capture on the screen, I'm going to say 10 minutes. Is that right, John? Probably 10 minutes,
10 or 15.
10 or
Yeah.
15 minutes. Okay. So
That's
here's
why we've
what
got to
we-
keep our scopes set up, guys.
Yeah, you turn on the scope before you turn on the coffee pot in the morning.
Yeah.
So I'm just going to zoom in here. What John has, if you guys will notice, I'm assuming everyone's familiar with Pico 7. I just started Pico 7 about 2 weeks ago when Darren and I first talked. I was reluctant to change because I hate change. I'll be honest with you. And I've become very proficient and confident with Pico 6. And guys, if you're not familiar with 7 yet, don't sweat it. It's a piece of cake. The layout's just a little bit differently. But what you realize what they tried to do with this program, you'll understand that everything becomes intuitive. Where the buttons are located, you'll figure that out. So again, this is my zoom box. I can blow it up like this. I can keep it totally minimized, or I can kind of blow it up halfway. Oops. like this, and just leave it as is. So what I have is the ability to zoom here. So what I like to do is the way John captured this is what I call a zoomed out view or a trend view. I like to see cycles happen over and over and over again. When it comes to your lab scope setup, Picoscope is very capable. It's got a ton of sample rate, probably the best ones out there compared to other scopes, even compared to ATS, for instance. We don't need a ton of sample rate for a very, very slow transition like we see with in-cylinder pressure waveforms. However, what you will notice when you zoom in on what I call a zoomed in event or a detailed event, when I zoom in on one cycle, these changes will tend to become muted. So if I go to this channel here and I go to this, I can enhance my resolution. So right now, vertical resolution is as follows. If you could picture vertical dots, okay, at 12 bits, there's X number amount of dots from the bottom of the screen to the top of the screen. The more dots I have, the more accurate I can draw a representation of what's being measured. And if we can go back to when we were children and we used to play those games where we would connect the dots, there'd be a picture of an apple and it was simply represented by dots on the screen. And we had to connect dot number 1 to dot number 2 to dot number 3. And by the time we got to dot number 100, we drew a nice picture of an apple. Does that make sense? So with 100 dots, if I could draw something that represents an apple, what would that apple look like if I took away 75 of those dots and only gave you 25?
Oh, great.
Pretty awful. Probably look more like a square. You know what I mean? Very octagonal. So the point is, the more dots I have, the better representation of the picture I have on the screen of what's actually being measured. Now there's a trade-off. I can ask for more dots, but this scope has only so many dots. Let's say it's got a gazillion dots. The more dots I ask for right now, the less I have over time. Does that make sense? So if I'm trying to capture data over the course of a half hour of elapsed time, I'm not going to be able to have that dot rate at the same rate because there's that trade-off there. You got to have one or the other. Do I want to capture more time or do I want to capture a prettier picture? With that
That's where
being
the
said,
buffer comes in.
that's where your buffer comes in, and you can fill your buffer quite quickly. In this case, it does not really matter because this is a relatively slow signal, even at what'd you say, John, 3,500 RPMs? What were you measuring here?
Yeah, 3,500.
So I'm going to go here. And I know John said 3,500. Keep in mind, these cursors are representing one complete cycle. So hertz is cycles per second, which would yield us 1,300 RPMs. Now, John just said this is like 3,500. Well,
I was trying to get to 3,500.
John, you didn't do nothing wrong. My point is this. One cycle should be one rotation of the crankshaft. One engine cycle is 2 rotations of the crankshaft. So basically one rotation is one rotation of the camshaft. There's your 3,500 RPMs right here. Does that make sense?
Yep.
So don't get confused. This is one engine cycle. But according to one engine cycle, they would call that 3,500 RPMs because it takes 2 rotations of the crankshaft to make one cycle.
That's just
At
a
30
crude calculation using time, isn't it? That RPM
it is.
measurement there, yeah.
And I've seen people goof up and not realize like, oh, wait a minute, a crankshaft has to go around twice for one cycle. Whereas if we were talking about a camshaft, yeah, we'd only go around once. So my point is, I just wanted to demonstrate the uses of the cursors and what is yielding us here. But what we see here, playing games with the cursors, I'm going to get rid of this again. We've got peak compression of about 75 PSI. Now, something else you can do here is this. You can command where you want your cursors to go. So let's say I wanted to go here and type in 0 PSI. It will automatically put my cursor at the 0 mark. Does everybody see that? So this is at 0. I'm going to grab my other cursor and drag it down to peak pressure at the point of top dead center of the exhaust stroke. And that's almost 30 pounds per square inch. Now, let me back up for a second. What I typically like to do is take the cursors here. Oops, let me go backwards. That was an accident. I'm going to click on my rulers tab. And I'm going to turn on my phase rulers. Now, what that's going to do is allow me to drag this and drag it, I think, to top dead center compression, which would be represented by the peak of that tower. And then to the point where the tower repeats itself in the same spot. Anytime something repeats itself in the same location, it's the definition of when a cycle begins and ends. So we'd see all 4 strokes at the end of the cylinder, the 4-stroke internal combustion engine process is occurring. Our expansion stroke, our exhaust stroke, our intake stroke, and our compression stroke. And we could see here that our peak exhaust pressure is indeed 29 PSI. Now, if an engine cannot exhale, can it inhale? In other words,
Not as well.
not as well. Watch my chest. If I inhale as much as I possibly can, and then try to take a deep breath again without exhaling, can I fit anything else in there really?
Nope.
I can't. So if my combustion chamber is filled with inert, spent exhaust gases that have no more oxygen left in it and no more fuel left in it, how can I possibly fill it with combustible gases like fresh air, oxygen, and fresh fuel? I can't. This is where that low power condition comes from. This is where an acceleration, a change in throttle position does not yield us any extra output from the exhaust stream. And the way John accelerated this vehicle, he's clearly captured the fault. Does everybody see that? We've got 30 PSI of back pressure. Now, just to play games here, I don't want to use this waveform because there's a lot of things that change when you have the throttle open, and I'll explain the method to my madness in a moment. But I'm going to pull this waveform off of here. And I'm going to put the new one on there, if you don't mind. So, John, you determined that the exhaust stream was restricted. You determined
Yeah.
it was a catalytic converter. You got permission and you replaced the catalytic converter and you repeated the test. Is that correct?
Yes.
And
Exactly what I did.
I mentioned that because anytime you capture a fault, no matter what test you're using, whether it's fuel trim or whether it's an ignition waveform or whether it's pressure testing, anytime the fault is captured, please repeat those same tests, all 5 of them, after you fix the car, because you're going to learn to understand what good looks like and what bad looks like. And that only happens when you've captured that fault, whether it's a fault or it's a fix. So here, John has displayed his buffer has 4 screen captures filled. So we've got 0 seconds all the way to 1 second. So John has 100 milliseconds per division. As you can see here, 100 milliseconds per division, 100 times 10 divisions is 1 full second of on time. Now, John did nothing wrong here, and he's clearly captured the fix. Again, we've got cycle after cycle on the screen. Again, that's the way I like to view things, in a trend view, seeing cycles happen over and over again. He's captured peak pressure at about 50.8 PSI, and exhaust pressure at idle here, it looks to be idle, I can't tell from this screen without putting up cursors, of about 1.2 PSI. 1.2 is a lot better than 28 PSI, isn't it?
Absolutely.
So this engine can now exhale, and because it can exhale, it can now get the fresh air and fuel in. His volumetric efficiency has returned, and as a result, the engine performs as it should. So this is buffer number 4, waveform number 4 in a buffer. I'm going to go back one more. There's 3, there's 2, and there's 1. So there's one thing that is missing from this. And again, it wasn't necessary in this case because John captured the fault. But in my idea, this is still more of a bird's eye view. We can't see the forest for the trees. We're way too close. So what I like to do is zoom way out, and I like to capitalize on the power of this picoscope. So I'm going to pull over a different waveform from another vehicle and demonstrate John's same technique that clearly captured the fault successfully, but just from a different perspective. First of all, I want you to see we've got not 100 milliseconds per division, but 2 seconds per division, and a sample rate of 5 million samples per second. Now, we can ask Picoscope to gather as many samples as we desire. It doesn't mean the scope software will allow it. It'll say, I just can't do that. I'm not capable. So it's going to do the best job it can. And what we've actually captured was 300,000 samples per second, which is way more than enough for a slow signal like a pressure transducer signal. What we have here, again, at 2 seconds per division, we've got a total of 20 seconds on the screen. And here's why this is important. And this is where you guys want to take notes of this. Anytime I am capturing pressure, especially in cylinder, I want to see pressure when the engine is cranking, as I do here. I want to see pressure when the engine starts and is at idle. I'm going to switch buffers, switch waveforms now to the next buffer. I want to see how the engine breathes under snap throttle conditions, like we have here. There's one snap, it returns to idle. There's another snap and it returns to idle. You can tell by the increase in pressure as the throttle plate opens. Oh, by the way, also when the throttle plate opens, look what happens to vacuum. Here's peak vacuum right here. Oop. And here is what happens when the throttle plate opens. Vacuum goes away. Why? Because we got rid of that restriction. Those pistons can now inhale freely. So there's no restriction, meaning there's no pressure drop. The pressure drop is what makes the vacuum. I hope that makes sense. So again, buffer 2, we've got idle, we've got cranking, we've got idle, snap throttle, return to idle, snap throttle again, return to idle. We can increase RPM. And in this case here, we've power braked the vehicle. We've stepped on the brake, we've put the vehicle in gear, and we very carefully open the throttle plate and allow these cylinders to breathe without allowing the engine to accelerate tremendously. This is the maximum amount of load you can put on the engine. You can do this all in the work bay. And on very, very, very small occasions, I have to take this vehicle out on the road, throttle to the floor, and beat the ever-living snot out of it to capture a breathability fault, like a very, very, very minor restriction in a cat. But most often than not, you can do all this right in the bay. Think of it like this, guys. I'm working on a big truck. What do you guys call it? A lorry, right? I'm working on a lorry. Okay. And I don't have a little 2-inch exhaust pipe. I'm dealing with a big pipe like this, right? Assuming an engine has a restriction, excuse me, a catalytic converter or an exhaust stream has a restriction. What's going to be easier? What's going to show the restriction easier? A small pipe or a large pipe?
Small pipe.
A small pipe, right? Because there's less area to fill. A restriction only becomes a problem when it's truly a restriction. And if that exhaust pipe is not filled to capacity, the restriction means nothing. Make sense? I could put my finger over the spigot on or what do you guys call it? A water tap, right? I could put my finger over the water tap and cover it 90% of the way. And if I just open up the valves a little bit so water will trickle, the restriction of my thumb means absolutely nothing. But when I open it up and I ask for more volume and I start getting sprayed with water, that's when that restriction becomes a problem. The same holds true with any type of restriction.
Getting some volume of gases down there.
That's exactly right. So
show it up,
Darren, I had a really close friend of mine from Florida call me one time and said, Brandon, just like John here, I 100% know I got a catalytic converter restriction. I know I do. It's in all the data. However, I wanted to prove it with the pressure transducer. And guess what? I did exactly what John Lamp did, and it doesn't show a restriction. And then I snapped the throttle, and that doesn't show a restriction. I don't understand. And I said, what are you working on? He told me a big lorry, right? A big truck with a big pipe like this. I said, do me a favor. I want you to climb in the truck in the bay right now and put the car in gear. And I want you to hold the throttle to the floor for a few seconds. And after a few seconds, the exhaust restriction started to reveal itself. Does that make sense? Because he had
to fill up. Yeah.
Right. He had to pump enough air into that system for the, and he could have repeated this process on the road when he felt the symptom. Does that make sense?
Mm-hmm.
So what I'm getting at, guys, here is capitalize on the power of your scope. The Pico scope has the power of capturing 400 million samples in a second at its fastest capture rate. That's not what's happening here, but certainly 20 seconds of capture time will yield you enough sample rate, enough samples available to capture cranking, start and idle, snap throttle, return to idle, snap throttle, return to idle, a power brake condition, and then return to idle again. You have all the information you need. You drive the car one time, you operate the vehicle one time, and then you go home and you drink beer and you eat pretzels and you analyze the data, and it's all here. More often than not, in a situation like John had demonstrated, hold on one second. Yikes. had demonstrated for us here is he said, hey, look, Brandon, I got 1 second of data here. And I go, uh-oh. He's like, what? Well, the fault is not visible in this picture. However, you only have 1 second of capture time. So I tell him, go back and change your settings, put 20 seconds of capture time on the screen. And then suddenly they got all the time in the world to manipulate the vehicle and not lose any data. Because when we're zoomed in, it comes in and it comes out real fast and we miss stuff. Does that make sense? So the idea is to put enough time on the screen that you can capture your fault. And we have to capture the faults under different operating conditions because of this. If I have a cylinder with a leak and I'm cranking the engine over, it's easily visible. If I start the car, suddenly that leak isn't visible. It's not visible. It's not very readily apparent, I should say. And people say, why? Or they send me the running waveform, the idle waveform, and I say, I don't see the fault. Send me a cranking waveform. And they said, well, I didn't capture it. I said, go back and capture it and send it to me. And suddenly, remember those pockets we talked about? A huge difference. Those pockets, I forgot to mention, should be about 2 to 4, maybe 5 PSI difference from one another at most. Typically at idle, they're almost identical. When you start getting a leak, they start to pull away from each other. And I've seen leaks as far as I've seen 13 or 14 PSI difference in pocket differential, if that makes sense. That's how much, but you start the car and let it idle and the engine is suddenly turning 4 times faster than it was when it was cranking. And there's not enough clock time for that leak to exhibit itself in the waveform. Does that make sense? The piston's moving so fast, the leak doesn't have time to be a leak. Does that make sense, Darren, the way I explain that? So here's another
You've got to
example.
put it under load and send some.
I am using an old Snap-on Modus, and this John, you remember this tool? I had it. This thing's
Absolutely.
20 years old, but John, this is where John and I started practicing on it. And Dan, I don't even know if Dan's still with us in this presentation.
No, it's not.
Okay. But we would stay late after work and start messing around with no good vehicles. And once we realized what good looked like, bad stuck out like a sore thumb. So you guys can see here. Here's top dead center. Let me see if I can zoom in on this a little better. Here's top dead center compression. We go back on expansion, our exhaust valve opens. Here's our exhaust plateau. Our intake valve opens. We go back on the intake stroke and then we go back on compression. So that's one full cycle. And another one, you could see as I snap the throttle, a couple of things happen. First of all, that vacuum that was down here disappeared. How do I know that? Because the throttle opened up and that's why this area is elevated here. And we got more air in the cylinder. How do I know that? I know that because compression jumped off the screen. When we open up the throttle, that cylinder breathes better. The more air we get in the cylinder, the more pressure we can build. It went so high, it jumped off the screen. But really, I'm not even concerned with that. I can also see the RPM picked up. Why? Because look at the frequency, how spread out this is and how close together these cycles become. It's because the engines speed up. But what am I really looking at here, guys? This is a snap throttle event. What's catching your eye here? Here's top dead center compression. Here's our exhaust event. Watch my cursor. What am I pointing at here?
We can see that exhaust event, can't we?
Exhaust is building up.
Exhaust back pressure.
Pressure. Yep.
This is what I'm looking at here. 30 PSI
30
back pressure.
PSI.
Now
Wow.
I'm going to repeat this. I'm going to drop the catalytic converter, replace it, and repeat the process. Check this out. What do you see here? Look at that back pressure. Now check this
It's
out.
dropped way down.
Is it possible this could be what I described earlier as just, this is pretty severe. So I doubt it would be this bad. But remember when I said when we're measuring back pressure through the spark plug hole, technically we're measuring pressure in the cylinder. We just like to understand that pressure in the cylinder is going to equalize to that of the exhaust. But if the problem is in the cylinder, you're going to see the same thing, back pressure. So after I got used to doing stuff like this, let's pretend I had John's car, that 2008 CRV. And I pulled one in and I did this test one night after work while me and John were eating pizza. We're just messing around and doing snap throttle testing because we learned it in the seminar from Mechanic Mindset. Now, and then we go back in here and we repeat this on a known good vehicle. We're like, look at that. We could see pressure increasing. The vacuum disappears because our throttle plate opened. Our cylinder fills with air because compression went off the screen. Our engine RPM picked up. But look, our exhaust plateau never climbed more than maybe 1 or 2 PSI.
PSI. Yep.
Now look, then I see this known good home run. Excuse me, I see this bad one. You could see this from across the room. Back pressure, instantaneous. Everybody starts running around, high-fiving each other because they're excited because they learned something. And they didn't learn it from class. They learned it because they taught themselves by evaluating known good vehicles. Uh-oh, what did I just draw on my screen there?
It's working now.
Yeah, right? It's still glitched. I'm not
But
gonna,
yeah,
I-
that's really good, because like the specifications of that scope, they don't look like they're really high.
That's
No,
a
and-
graphic multimeter, really.
Right.
Right.
Okay.
Advantage.
What I'm currently looking at on this lab scope is Snap-on does something very different. In Pico's case, we can put 20 seconds of time on the screen and we can use our zoom window. We can zoom in, right? You
Mhm.
can't do that with a Snap-on device. It's best to zoom in on a Snap-on and put maybe 50 milliseconds or 20 milliseconds on the screen, total sweep time, 2 milliseconds per division. Capture the information in the buffer and then zoom out.
Yeah.
So I have got 4,000 milliseconds on the screen, 4 seconds, if you will, on the screen. And I was capturing at 500 milliseconds for a total sweep, 50 milliseconds per division, but I zoomed out 8 times. Again, understanding how the tool I'm using works. It doesn't work like a Pico. It works the
That's it.
opposite.
Yeah. And
So
that's
if I
it. And
did-
that's just using, like you say, using what you've got, understanding what you're looking at, and then
That's exactly it.
you can use it. Yeah.
I could simplify that further. I use a Fluke DVOM, and the update rate on that DVOM, at least to the display, is fairly rapid. However, I could put that tool down and go buy a different DVOM that's perfectly capable, but the update rate of the screen might be every 2 or 3 seconds. So as I'm looking at a circuit with my DVOM, my Fluke meter, it updates and it stays there and it flickers like this. But then I put that other tool on that same circuit and it updates and it updates and it goes from 12 volts to 8 volts to 4 volts to 8 volts. And I'm thinking there's a problem with the circuit, and there's really not. I just don't know. I'm not familiar with how that tool responds. Does that make sense? So if I don't practice with my tools, I don't understand, maybe I understand what I'm teaching here, but what my tool is showing me, I can't decipher that as being normal or an actual broken car. Is it the way the tool is responding, or is the car really broken? So I hope that makes sense. And I apologize again for this yellow streak on the screen. My PowerPoint presentation, I should technically close it and relaunch it. It's glitched, but I don't want to do that at this
Yeah,
point
it's
in time.
powerful stuff. Yeah.
Thank you. So listen, before I take any questions, I know we covered a lot of information in a very short period of time. And it was not my intention to push this information in and out of your ears and totally overwhelm you or make you feel like, oh my God, I don't understand it at the level this guy does. Maybe this isn't for me. This was nothing more than an introduction to let you know the power of utilizing pressure transducers when coupled to a lab scope and allow you to make some truly cool diagnostic decisions before taking anything apart. As a matter of fact, I was first introduced to England on service technical side by way of a good friend of mine. Does anybody know the name of Ryan Colley out in the Taunton area in the south of the country? Good friend of mine. He initially approached me with an Audi S8. And for those of you that are familiar, the timing components on this longitudinally mounted powertrain are sandwiched between the bell housing of the transmission and the engine, meaning he suspected he had a timing issue, but didn't know how to prove it without investing the 30 to 40 hours of labor time to find out if he was correct or incorrect. Every shop in the area told him, don't be crazy, mate, get rid of the car. Tell the customer to sell it. But he thought he could prove it otherwise. And through pressure transducer diagnostics and the power of the internet, he shared the waveforms with me. He and I went over the waveforms together, and he was able to conclusively tell that he had a timing issue due to a VVT, right, a variable cam timing actuator fault, and successfully disassembled the engine with 30 man-hours of labor time invested and found the root cause problem and repaired it, made thousands and thousands of pounds on the job, or I should say hundreds and hundreds of pounds on the job, and got the vehicle back to the customer where every shop in the area told the customer they need a new vehicle. So this stuff really, really works. What I have on the screen here is just a screen capture of where you can find my book if you're interested. I have the book available. It's an 8-hour course with hundreds. Hey, there, Clive, Ed's got it. 8 hour. What do you think so far? If you wouldn't mind, turn on your microphone. If you have a microphone, that'd be wonderful. I'd rather get some perspective. You'd have to turn your mic on, but we see this book. I tried to pour as much descriptive information as I could in it. And the way I'm talking to you guys today is exactly how that book is written out. It has almost 30,000 words of annotation in the book. And it's, I think, 350 pages with 14 case studies, live case studies like we went over today, of all different kinds, of catalyst restriction, of jump timing, of worn cylinder walls, of cylinder leakage to the cooling system, compromised head gaskets, jumped timing, bent connecting rods, worn cam lobes, collapsed lifters, you name it. I had my hands on it, and we break it down step by step, not even just the cylinder analysis, but the logical approach, the diagnostic process, beginning with the scan tool and gathering preliminary data so we can develop that diagnostic workflow, that logical path that leads us to the answer successfully every time in the most efficient manner possible. Again, that's what we're all after. So that book's available here, hands-on, a live book for $124 US, or as an ebook where you can read it, flip the pages virtually and read it, available at AES Wave. And there's the link right there. So if you type AES Wave, I tried to capture the link itself and post it in the chat, but
I've put it in there. Yeah.
Okay, great.
So the link's in the chat, and I will, this will be a lesson in the live section of our site
Perfect.
after, Brandon. So all the links and details will go in there as well. So
Excellent.
yeah.
And one thing I do want to put out there, Darren, guys, I am on Facebook. I'm on Facebook Messenger. I'm going to put my email address here. If you stand by just 1 second. I lost my chat box. There we go.
So yeah, so much value in what Brandon shared today, and even in just I suppose just over an hour that we've been talking. I've got a copy of that book as well, the ebook.
Excellent.
And there's just so many like case studies in there, and all the I suppose the applicable data that you can actually take back and have a look at on the car. So this session will be definitely one to review again.
Excellent.
Has anyone got any questions for Brandon?
While you're thinking of questions, fellas, that my email address, you can reach me anytime there, and I'm always happy to help. So no question's a stupid question. Any questions about anything, feel free to reach out and I'll do my best to help you out.
Really appreciate that, Brandon.
Of course. Happy to help.
So we had a couple of questions that came in.
Yes.
Can we, sorry, let me just find one here. So someone asked what type of pressure sensor they should invest in.
My question to you with that question would be, what lab scope do you have? So if you already own a Pico scope, for instance, no questions asked, I'd recommend a WPS 500. A little pricey, but worth their weight in gold. And again, they can be applied to any vehicle out there. If you have a Snap-on, for instance, I would not recommend the Snap-on transducers. I've used them and I don't care much for them. I think they're very expensive and they don't have, they auto zero and they don't do near the job that another transducer would do. I would seek out, if you are a Snap-on user, a Fluke PV350. You do not want to buy one of those new. The new ones, they've removed one of the computer chips that gives it the frequency we need to report this pressure data accurately. An older one, however, does have this computer chip in it, and it allows us to see an accurate representation of the waveform. If you buy one brand new, it's going to look like the London city skyline at night, just up and down and no real definition. It's not going to be useful at all.
Brandon, take a look at the one Darren has, the Auto Ditex. That looks good.
John, and you've used that, right? That's what you're using?
No, I bought the WPX knockoff
Okay.
from China. It looks just like it, and it works. There's 3 different settings.
So this is what you're displaying here, correct?
Absolutely.
Okay.
That works real well. That was $274.
That's compared to the $800 US or $1,000 US for the WPS kit, and not knocking
Correct.
any one of these. There are many transducers that are highly capable out there that I simply have not used. So I will never knock them. I just have no experience with them. And I don't want to tell you guys something's great if I haven't used it and thought it was great.
I
But-
used to have the Fluke one. I got rid of it and bought that thing.
Excellent.
That works real well. But whatever you buy, just use it.
That's it.
Yeah.
Use it and
Yeah.
get used to it. Absolutely.
Yeah, brilliant. So yeah, Rob had actually put a few questions in there, Rob, and I think I was just looking at your inputs and I was reading through them. I thought, I think we've captured that. We looked at blocked cats DPF. We discussed about carbon buildup with the it'd be slower to you'd get
Exhaust stroke.
yeah, so that you wouldn't get the sharp changes in valve events. Yeah, correct. Yeah, and I think someone else asked about checking head gasket leaks with the WPS 500.
Yes, absolutely. If you give me a moment, I have one here. I can demonstrate. Just bear with me one moment. And I'll see if I can pull it up on the screen. I'm listening to your questions. Go ahead. While I'm doing this, I can listen and do this at the same time.
Okay, so someone asked about what tips can you give to identify a slightly worn cam or a very small amount of play in the valve train?
So anytime there is an issue with a cam lobe or a cam or a lifter, you are going to affect the duration. So by measuring when a valve opens and when a valve closes will effectively give you the duration in degrees, or how we're looking at on a lab scope is time differential between the two, delta time. So if you have a worn lobe, anything that is worn is going to open later and it's going to close sooner, if that makes sense.
Yeah, because it's not going to be the profile is not going to be the same, is it?
That's correct. It's going to
Yeah.
change. And when compared to a known good, as in another cylinder next to it, it's going to stick out like a sore thumb. So bear with me 1 second. I am pulling up a pressure issue inside a cooling system. But again, I'm listening to you, Darren.
I think the known goods as well are going to be quite important as well for some of these more minor issues. So like we just mentioned about the possible worn cams, when you might have a slightly later open and an earlier close.
Yeah.
That might actually look all right if that was the first waveform you were going to look at. So I think, that having that overlay or that reference could be quite important for that. Would you agree?
I would. And the one thing we did not touch on today, because there's simply no time to get into this arena. I am always out to look for information collected from a common point. In other words, for the same reason we used to analyze ignition waveforms in a paraded format, comparing one to the other, right? One to the other 8 cylinders or one to the other 4 cylinders. I'm going to look in an intake manifold for pulses to compare how one cylinder's contribution to the intake manifold differs compared to the other cylinders' contributions. Does that make sense? Is my PowerPoint still present on the screen for you?
Yes.
Yeah, I can see the
Okay, so
cooling system
we-
piston chart. Yeah.
Have we ever seen an engine where we crank it over and it is so tremendously failed for a head gasket that it puffs smoke out of the radiator? You can see exhaust gases leaving the radiator as the engine's cranked over.
Yeah.
What you see on the screen here is one of those. So what I did was, again, ignore this yellow line. I drew that inadvertently on the PowerPoint and I can't get rid of it right now. So I'm sorry. What we have here, we've got an amp clamp, right? An amp probe connected to a battery cable representing 6 cylinders load on the starter. Cylinders 1 in yellow.
Relative compression.
Right. We call that relative compression. Cylinder 1 in yellow. That's an ignition strike. I use that as a cylinder sync or point of reference. And if I know the firing order, 1, 4, 2, 5, 3, 6. This is 1 and it has a low peak. 4, 2, 5, 3, 6, and 1 is low again. 4, 2, 5, 3, 6, and 1 is low again. Every time cylinder number 1 has a low compression event, I am using a delta sensor on the radiator filler neck. A pulse, a pulse, a pulse, a big pulse as number 1 leaks to the radiator and it recovers. A pulse, a pulse, a pulse, a big pulse. As you can see, 1, 2, 3, 4, 5. 5 full cycles, 10 rotations of the crankshaft. This is a zoomed out view, right? I've got 5 seconds of screen time captured because I want to see it repeat, 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 repeat. And if I want to, I can zoom in and analyze it and put a piston chart on it. So I'm not going to go over this, but I can do stuff like that. And you can learn to do that the same. And all of that's in my book.
Cool. Yeah. So yeah, I think someone did ask about piston charts, and we'll be adding a lesson into our automotive oscilloscope diagnostics course on piston charts and the delta pulse pressure sensors as well, and things like that. So that's all coming as well, guys.
Excellent. And it's the power of these auxiliary tools, the cursors provided by the scope software, the piston charts, having adequate service information about firing order. I will make this point, gentlemen, there are 30 known, at least that I'm aware of, at least 30 different firing order configurations. So if you are not 100% sure, please don't guess. Because if you use information like what's found on this piston chart here, and you have not plotted this chart correctly, in other words, you've chosen the wrong firing order, you may find yourself removing the wrong cylinder head. You thought the problem was
yes.
on the right side of the engine, but it was really on the wrong side. And where did you goof up? The only thing you did wrong was punch in the wrong firing order. Your approach was correct. Your diagnosis was correct. You just made a mistake on which side to remove. So just don't guess.
Good information.
Yeah. Learn from my mistakes.
And don't guess, I think, is a good one for everything when it comes to diagnostics, isn't
Yeah,
it?
that's a good
You know,
blanket
That's
statement.
what all this is about, is just proving it and going to the customer and saying, you know, this is what's wrong with your car. I know it.
Yeah, absolutely.
Brilliant. Someone just asked if you have to disable the water pump for that test. Is that?
No, and another thing you don't have to do, you don't have to disable the water pump. You do not have to seal the Delta sensor hose to the surge tank or to the radiator, the degas bottle. It could simply lay in the filler neck, almost as you would a gas analyzer, fellas. If you were using like an MOT gas analyzer and you stick it in the tailpipe or you stick it over the radiator, certainly you don't want coolant inside your Delta pressure transducer. And
That's
it's
how
actually
sensitive they are, right? They're so sensitive.
It is. And it's actually better to have a little bit of air in there, like suck some of the fluid, the radiator fluid out to leave, because as that water is displaced up and down the radiator, that air is going to be displaced as well. That air is
Yeah.
going to be displaced. Almost if you're using the speaker phone on your phone and you hold it close to your face, you can feel the air pulses from the speaker if you have your volume cranked up loud enough.
Yeah,
It's
yeah,
that
yeah.
same displacement of air that the sensor is picking up on. So it's good to have that cushion of air, that little bit of low radiator fluid. You don't need to sew it up. That big cushion of air is going to provide that buffer to give you a nice waveform rather than too much activity.
Awesome. Okay. So has anyone got any more questions for Brandon before we wrap it up today?
Yeah, one more. I'm a Japanese specialist, Brandon. How can I work on Hondas quite a lot? And obviously they've got adjustable valves. How can I prove a vehicle would need adjustment without going in cylinder?
Okay, well, if you give me a moment, I'm going to pull up some information. So what we have here, what comes into play is what you're describing as valve overlap. Valve overlap is defined as any time the exhaust valve and the intake valve are opened at the same time. Anytime, this represents when an exhaust valve opens, and this represents when the exhaust valve closes. If I tighten the exhaust valve, it's going to open sooner and close later, meaning my duration is going to spread out. Does that make sense? If I give more clearance, I loosen the valves, my exhaust valve isn't going to open here. It's going to open later and close sooner. So anytime you have valve clearance issues, your duration is going to change. It's either going to diminish because the valve is too loose, too much slop in that rocker, or the duration is going to increase because it's too tight.
Like what we said earlier with the worn cam, so open later, close early.
Right. So this is a very crude drawing, and I had to take a picture of a picture and then draw on it to increase the color contrast between the two. So this was old technology. This waveform's at least 12 years old. So pardon me. But what we have here, this represents changes in the intake manifold as an engine is cranked over and over again. And Grant, what you can see here is you see something that represents the top of a letter M here, the up and down nature.
Yeah.
Okay, this represents valve overlap for number I can't tell here. Looks like number 5. This is for number 3. This is for number 6. This is for number 1, but look at number 4. See how it
Right.
doesn't look like these? And then look at
Yeah,
number
yeah, yeah.
2. This is represented by a variation in valve overlap. So this is before. Watch what happens. I'm going to adjust the valves, Grant, and watch what happens. I'm sorry, I lied to you. This was measured at the tailpipe. You can do the same at the intake manifold, but this one was acquired from the tailpipe. I simply put this in the tailpipe, just as you would a gas analyzer in the MOT, and I crank the engine over, and this is what I acquired. I'm going to adjust the valves and repeat this process. And now look at my waveforms. Don't they all look uniform?
Yeah,
So the point is,
that's
Here.
awesome.
here's number 1. This is number 1 top dead center compression. This is going down on the power stroke or the expansion stroke. This represents bottom dead center. However, the exhaust valve does not open at bottom dead center. It opens about 45 degrees before. So what happens in the tailpipe? When I open up the exhaust valve, the vacuum in the cylinder, listen here, I pull a vacuum in the cylinder. Listen to what happens when I take my thumb off of this. You hear that?
Yeah.
That
Just
suction-
drops. Yeah.
That suction goes to the tailpipe. Look what it does. It creates that suck back. So this suck back right here is because the exhaust valve opened. And when did it open? Right here. Look at the distance from this black line to when the valve opened. You see that?
Yeah.
From here to here. Now look at this one. It's about the same. Look at this one. It's about the same. This one is about the same. They're all about the same. Do you agree with that?
Yeah.
So when I have one that's too loose, let's say it was this one, the pull, the suck down doesn't occur here. It might occur somewhere over here. Or it doesn't occur here if it's too early. It's not going to be here. It's going to be earlier. Does that make sense? So-
So because of your overlap as well, you'll get the same pattern, whether it's an exhaust or the intake.
It'll look differently, but you should have the same repetitive nature, if that
Okay.
makes sense. So I'm
Yeah.
going to see if I can show you a different one real quick.
Was that
Here we
delta
go.
sensor or?
That is
WPS
indeed a
500.
delta sensor.
Yeah. Okay. Yeah. Cool.
Which I've got. Brilliant.
Yeah, such powerful stuff from such a small, cheap tool.
It
Yeah.
really
Yeah.
is. I bought one for about $85 and it works phenomenally.
You should check out the video where I make one, Brandon.
I've seen some really cool
Yeah.
stuff with people making them.
Mine's not cool. Mine's
phenomenal.
crude.
My first one was made out of my daughter's baby bottle.
Okay.
So here's one. I'm just going to introduce this to you real quick. And then we'll wrap it up. Let me see. Can you see that? So going back, I've got a vehicle with a misfire. It turned out doing a relative compression test that it yielded me a dead cylinder. And rather than pulling spark plugs out because they're in the back of the engine or in the front of the engine here, very difficult to get to on this year make model. I didn't want to burn my arms. So I decided to sample right here with a vacuum transducer and connect it to the intake manifold. So what we see here, this is an ignition command. This is a waste sparks event, and then another ignition command, 720 degrees. These are intake manifold pulses. We can see they're not the same. I partition it a handful of ways, 6 ways, because there's 6 cylinders of this engine. And this is a vacuum transducer. Remember, it's upside down from a delta sensor. So this is a vacuum pull. There's one, and here are the other ones. They're not all the same. So using a piston chart, I know cylinder number 2 is my dead hole. Here's a vacuum pull from number 3, according to my chart here. This is a vacuum pull for number 4. There's a vacuum pull for number 5. And then all of a sudden pressure drops again. Here's a vacuum pull for number 6. The vacuum pull for number 1, but number 2's vacuum pull, what's wrong?
Nothing.
It's
Nothing.
missing. There's nothing there. It's not contributing to the intake manifold. So when I go in cylinder, I can see here, I go up on compression. Here's my vacuum. I go up on compression. I come down. My pockets are even. What's it say about cylinder leakage?
No leakage.
No
There's
leak.
no leakage because my pockets are even. I go up here on what would be my exhaust stroke. I have a misfire because I have 12 PSI of compression, but I have no leakage. Here, where my intake valve is supposed to open, there's supposed to be a drop in pressure. However, there's no drop. The piston is starting to descend against closed valves, and I'm slowly pulling a vacuum as the piston descends. Notice how this is all rounded. There's no valve event that popped open. So here's if I go back, this trace right here, I now have in yellow and I'm zoomed out. So you can see a little vacuum pull, another one, and then all of a sudden There's no vacuum pull for this cylinder, so my vacuum in the manifold degrades a little bit. And then when the next cylinder in the firing order has a successful vacuum pull, like we see here for number 3, my vacuum starts to recover again. So the end of this whole story is I have a misfire because cylinder number, I think this was number 2, has only 12 PSI compression. However, there is no leakage. The reason why I have no compression is because the intake valve didn't open and I didn't stuff anything in the cylinder to squeeze. Does that make sense? So the proof is there's no intake valve opening, and I could see that reflected also in the intake manifold because we lose vacuum there. This one is not contributing. It didn't take its turn. Picture us being in a skinny boat, a canoe going down the lake, and there's 10 of us in the boat, and everybody takes turns one at a time, overlapping as they row the boat down the pond. If one of the guys says, "I'm not doing it," we lose momentum momentarily. We lose that acceleration, and that's what's represented right here. I hope that makes sense.
Most of the engines over here, Europe, you probably noticed this from the European engines and stuff. They're all like 4 valves per cylinder.
Yeah.
So do you notice much difference if you lose one of those valves?
The only thing of significance there is this. So you're saying if I have 2 exhaust valves, for instance, and only one has a duration issue.
Yeah.
Okay, here's what you have to remember. The pressure transducer does not tell us what's wrong with the vehicle. It shows us pressure and how air moves in and out of the cylinder.
Mm-hmm.
It's up to us to analyze the waveforms and determine. That makes sense, right?
Yeah.
With that being said, if a cylinder can move the air, it can exchange that air without fault, our problem is not reflected. So let me give you, for instance, if I had an exhaust valve that had an issue, one valve, and there's 2, I wouldn't have a problem at idle. I probably wouldn't even have a problem accelerating to a certain RPM, but maybe at 6, 7, 8,000 RPMs, I'd start to blah, 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 feel like the EGR valve is kicking in. Because you know what I'm saying? Because at that point, one valve being open instead of 2 would yield me a restriction that is preventing airflow.
Yeah.
However, at idle, this is not a problem. For the same reason, when I said if I put my finger over the water tap and cover it 90%, if I only open the valve a little bit, that water can still trickle easily past my thumb. But if I crank the valve wide open, suddenly my thumb is a restriction and water sprays everywhere. It hinders flow.
It's putting the engine into a state where the problem is apparent.
Now, can you see why I recommend cranking the engine, idling the engine, snap throttle, and power braking, and sometimes even accelerating down the road for that same reason? One exhaust valve opening instead of 2 will not cause too much of an issue until I'm under very heavy acceleration. And by the way, a case study like that is in this book as well. I lost 1 intake valve, not 2.
Okay, excellent. Cool. Well, I think we will call it an end there. It's been like absolutely amazing having you on.
Thank you. I appreciate the opportunity. It's a lot of fun for me.
Privileged to come and join us. You know, there's a wealth of knowledge there in those couple of hours that we've just covered, and a bucket load more in that book that you can get hold of as well. So thank you very much.
Absolutely, my pleasure.
Thanks for coming. So
Good time, Brandon.
Thanks, Johnny. Good to see you.
Yep.
Thank you.
Yeah.
And thanks everyone for joining. I think that's the biggest session so far. So I think we've got 47 on at the minute.
Thanks, Daryl.
So yes, thanks for
Brandon.
You got it. My
participating
pleasure.
and coming along. The recording will be up soon. Okay.
Thank you.
All right.
Bye.
Got it, Scott.
Brilliant, guys. Thank you. Bye.
Take care.
Aaron, thank you.
Bye. Have a good evening.